So this wave function, y equals a sine omega x, omega like a curly W. Guys, focus in. Omega curly W. So what I want you to do is to investigate this. So then we're going to come back and have a look and see what you found out about it. So I'm just going to show you what I want you to do. When you put this into autograph, first thing to recognize is that you can't put capitals in. So what you type into autograph really is y equals a, type sine, sin, again you just get the lowercase, it recognizes sin as the sine function. But I want you to investigate the sign of everything that follows. So you must put the omega and the x in a bracket. There's no omega symbol there on the keyboard, so just use W to represent omega. So type in y equals a sine wx. And then I want you to plot that and confirm that one cycle is over 360 degrees or 2 pi radians, depending on which scale you're in. So I want you to, when you investigate it, I want you to look at the degrees and the radians and just see how the two work. So I want to just show you that before you get going, where those buttons are. So I'll put that up again in a second, but let's just have a look at this function. Here it is. I've typed in y equals a sine wx, and you can see that there with the wx in the bracket. Now, if I wanted to investigate this thing with degrees on the x-axis, then I need to make sure that degrees is checked here. If I want to investigate it in terms of the radian, then I click the radian button, and instantly you can see that the whole scale's changed. So to be able to zoom in on one part of it or one cycle, I would need to zoom in on the x-axis. So I stretch out this wave, and then I can start to see what one wave looks like. So again, if I were to go back to degrees, now it's far too big, so I need to zoom out on the x-axis to be able to get the thing back in so I can see it. Okay? So back to here, what I want you to do is to look at these questions here. Investigate what's the effect of changing A. Oh, it should be a G on the end of there. I'll do that in a sec. Investigate the effect of changing W or omega. And then if you've done that, while you're waiting for everybody to get up to date, it shouldn't take more than about 5 or 10 minutes to do this, but we'll see. As an extension, add this term alpha to the bracket and see what effect that has on the function. Not something you're going to be asked to investigate for the assignment, which is why it's an extension activity, but it's the last thing that we put into the wave function. So actually this here is the wave function as used in engineering. So the alpha does appear in there. So if I can just give you 5 or 10 minutes, maybe quarter of an hour or so, just to investigate the effect of changing A and W. So following our investigation then, if I want to plot one cycle in degrees, what would I sketch on here, Alex? What would I sketch to do one cycle in degrees? Connor. Yeah. Right. This is 360 degrees, right, Alex? That's one cycle in degrees. What's one cycle? Chance to redeem yourself, Alex. What would I sketch if I wanted to show one cycle in radians? Same as that. Any points I can mark on the graph? Yeah, midpoint and that point. Could you tell me what those values are if I'm measuring in radians? What's one complete cycle in radians? Can you remember? 2. No? No? 2 pi. Yeah. Okay. So what's this? pi, right, okay. So if I want to measure one cycle in radians, it's pi and 2 pi. That's what I'd expect to see. If I wanted to do it in degrees, 360 degrees, so the midpoint obviously would be 180, okay? Most of the time from now on, when we're looking at the wave function, we use radians, okay? We never use degrees when we're talking about these, because the radian gives us a fraction of a whole cycle, in terms of the circumference. 2 pi times the radius gives us the circumference, rather than just dividing it up into an arbitrary number of degrees. Ben, let me just put that down. So we're going to stick to radians. This is what we use. So radians with the wave function. So from now on, when you investigate the wave function on autograph, it needs to be in radians, okay? So if I now sketch this, and I want to sketch y equals 2 sine 1x in terms of radians, what would I sketch? Okay, so I would sketch my cycle. Here's one cycle. Points I would put on, any points I know. What would the top be? Right, so not 2 pi radians, just 2, because the 2 hopefully is the amplitude. So what does A represent in the wave function? The height of the wave or the amplitude, okay? If this is a 1, what would this point here be? Which would be? Right, 2 pi. Not 360 degrees, we're sticking to radians, don't forget, okay? 2 pi radians. What about this? Sketch this, and then mark these points on. And we'll look at them together in a second. So what would that look like? Just sketch it quickly what you think it would look like. Marking any points you know. So Ash, what do you reckon? Yep. Right, well done. Okay, look at this for a second. Because that's a 2, if you were investigating this thing, you would have noticed that actually within 2 pi radians, you actually get 2 cycles. So if I were to carry on with this wave, 2 complete waves would then be 2 pi radians. So what's one wave? Pi. Yep.
So the number opposite is relevant to how many cycles?
Yeah, that's right. This omega is called the angular velocity. Okay, angular velocity. What is it that's generating this sine wave? It's something that's rotating. And here it is. So it might be rotating. We generally talk about things rotating anti-clockwise. So it's rotating with an angular velocity, omega. And that's giving you an idea of the rate at which it's going round. So if you imagine this sweeping out, Gareth, then it's going at a particular rate round in this circle like this. And going round one complete cycle, it will sketch out this. Look, it starts at 0 here, goes up until by the time it reaches the top, it's reached the top there. And then it goes down to 0 again, back round to here. Well, that's the idea of this pen. Don't worry about that, Gareth. Focus on what I'm trying to show you on the board, please, okay? And then it gets to here, which is this point here, and then rotates down this way. So it gets to the bottom and then back up to the top again. So one complete turn of this is represented by one complete oscillation. Okay? So if I double omega rather, in other words, this becomes a 2, then I'm doubling the rate at which this is rotating. So I get 2 cycles within 1x. So what does x represent? What is x? What is x on this axis, really? As it's rotating round, what does that represent? No, not the frequency. It actually represents time. So within a certain time period, I'm getting, in this one, within a certain time period, 2 pi, I'm getting 1 cycle. Then I double the rate of oscillation, the angular velocity, and I get 2 cycles within that same time period. Or, what's the time for 1 cycle? Half of what it was before. That's right. So if I turn that into a 4, then I'd get 1 cycle over a half a pi. Yeah. Okay. So what's the effect of changing W? It gives me a faster rate of rotation, so I get more waves within one period of time, 2 pi radians, for example. Okay. So let's just summarize that. So let's just summarize that with 3 sketches. 1, 2, 3, 2 pi. So measuring in radians, this value, 2 pi, if I'm plotting time along here, that's actually a period of time. So what is 2 times pi? Pi is roughly 3.14, so 2 lots of that's about 6.18, 6.2 seconds. So in other words, this is roughly 6.2 seconds has gone by. Okay? And if I were to plot y equals a 2 sine x, or t now, okay? So instead of x, I'm going to write t. I would get this wave. With an amplitude of 2. Okay? Right, James? Let's put in a bit of mental picture of what's going on. Not a very good sine wave this time, but okay. If I now want to plot y equals 2 sine 2t, what would I sketch on here? Do this wave twice. So within 1 cycle, so it's a bit awkward to sketch, but let's see if I can do it. I've got to try and get 2 waves within that same period of time. I've doubled the angular velocity, so therefore I've got 2 waves within that same time period. And then if I were to try and sketch 2 sine 3t, this is an awkward one to sketch. I'm now going to try and get 3 cycles within here, so 1, 2, that's roughly thirds, so 1, 2, 3 waves within there. So again, this has, I've made it smaller, but this will still be an amplitude of 2. 3 waves within the same time period. So what would this point be here? 2 pi over 3, because 2 pi is the whole period. So this would be 2 pi over 3. Okay? Okay. Let's look again at these values. Let's look at this wave function. Y equals E sine Wx, omega x. Actually, let's call that a t now, because that's really what it represents. I just gave you the x because that's what you're plotting on autograph, but really that represents the time. So here is the wave function. Now omega equals 2 pi times the frequency. This is a formula that we came up with last year when we were looking at these things, which relate to angular velocity and frequency. So what's the relationship between angular velocity and frequency? There it is. What's the relationship between frequency and the period of a wave? The frequency is 1 over t, where t is the period. Which is the time for one cycle. And f is the frequency in hertz, which is the number of cycles per second. What I want you to do now is to go back onto autograph, and then I'm going to ask you the question, how can you read the values of A, F and T from autograph? How can I get values for A, F and T from a sine wave, or from a wave function? So in other words, if I had this, and you didn't know what function I'd put into the autograph to get it, so you've not got y equals 3 sine 2x or something like that, you had to work back and calculate what A and W were. How would you get it from that curve, from the point of view of those equations and our knowledge here so far? Okay, so I'm going to give you 5 or 10 minutes just to think about how you might come up with those values, A, F and T, from a wave. And then if you think you know, try it, okay? Try and confirm it by looking at your wave.